If I give you a circular current carrying wire, then at the center the magnetic field is given by mu naught I by 2r, where r is the radius. And if this has n turns, if there are n turns very closely wound, so that everybody can be told to have same radius, then if there are n turns, you just multiply by n. This is one important formula. Another one is, if you have a straight wire which is not infinite but it is finite and it carries a current I, then direction we know it will be like this. Okay, at this point it will be inside the board, here it will be outside the board. But if you want, let us say, magnetic field here, magnitude if you want, then what you do, first you draw this perpendicular line. First you have to draw that perpendicular line and find this distance. Let us call this distance is A. Then from the ends of the wire you have to draw these lines. Okay, then you try to measure this angle. This angle suppose is theta 1 and this angle is suppose theta 2. Okay, then the magnetic field at this point is given by mu naught I divided by 4 pi this A into sine theta 1 plus sine theta 2. So this formula again you have to remember. Okay, what if the wire was infinite both the sides? If it was infinite both the sides, then this line will become parallel to this line, because this point will be at infinity. So these two lines will become parallel. So this angle will be 90. This angle will be 90. Put here 90, 90. You will get sine 90 plus sine 90 will be 1 plus 1, 2. That 2 will cancel 4 here. So your formula, if it is infinite wire, then it will be mu naught I by 2 pi A, which we have done in the class also. Using Ampere circuital law, we have derived this formula, right? So that is how you can check if you have written the correct formula or not. Don't write by mistake cos. In some textbooks, you may see cos here. The reason why they write cos here is because they measure this angle. So if you write in terms of this angle, then sine will become cos. Yes or no? Because this is 90 minus this, right? So in terms of this angle, if you write, this will be cos. Also, one thing you remember, I have taken this angle positive and here this angle positive. So if it is opposite to whatever I have taken, you have to put minus. For angle, you have to take minus. Those students who want this to be positive and this to be negative, you have to put a minus sign here. But let me write this way only. Okay, students. So theta 1 this side is positive, I have taken. Theta 2 this side I have taken positive. So the first question says, a current of 1 ampere is flowing in the sides of a equilateral triangle of side 2 meter. The magnetic induction field at the centroid. At the centroid. So they have given you in the first question a equilateral triangle. Side is given as 2 meter. So let us call the side is A. So this A is 2 meter. Okay. And since it is equilateral, you know this will be 60 degrees, 60 degrees, 60 degrees. Yes or no? And the current flowing in the, you can think of this like a wire. The current flowing in the wire is 1 ampere. So what will be the magnetic field at the centroid? Now centroid means what? Wherever the medians will intersect. It may not be exact, but that's okay, right? So this is the point where we have to find the magnetic field. Let me call this point P. Now let us say current is this. So first let us check the direction of magnetic field here due to this current. Put your thumb here, curl of the fingers will give you magnetic field. So here magnetic field is out due to this wire. Due to this wire it is out, right? And due to this wire also it is out. Here, okay? Here it may be in, but here it is out. So we know due to each part, magnetic field here is outward. So we need to just add all the magnetic field produced by this wire, and this wire. So let us take one wire. So magnetic field due to one wire or one part of the wire. Which part? Let me call this AB. So one part of the wire which is AB. Let us find due to this part. So this is a finite wire. So first what I told you to draw perpendicular line which is this itself. So let us call this distance small r. Okay. And then from these ends you have to draw these lines. Already I have drawn. Then you have to measure, as I told, this angle. Here theta 1, this is theta 2. Now please understand this whole thing. See, this is 30 degree. This is 30 degree. Right? This is 90 degree. So this must be 60 degree. Similarly, this should be 60 degree. Correct or not? So theta 1 and theta 2 both are 60 degree for this straight wire. Understood or not? Okay. So what will be the magnetic field due to just one part? Let me write B1. What will be the formula? Mu naught I divided by 4 pi. Here what we write? Perpendicular distance, which is small r I have written, into sine 60 degree plus sine 60 degree. Plus only because this is this side, this is this side. So both are positive according to what I have done in the theory. Now R we need to calculate. This is centroid. You should know that centroid divides the median in the ratio 2:1. Okay. So this distance should be, R should be one third of this height. Okay. This should be one third of this height because the centroid divides the median in the ratio 2:1. So height, how to find this height? How to find in terms of A? A is given to us, remember. This is your A. Okay. So height I can find by using Pythagoras theorem. So root over hypotenuse square minus adjacent square. This is your adjacent, which is A by 2. So A by 2 square will be A square by 4. Correct? So that will be root 3A by 2. Take LCM and take square root. That means R will be how much? One third of this height. This height is root 3 A by 2, which will be A by 2 root 3. R will be A by 2 root 3. Right? So R also we have found. So let us substitute. So magnetic field due to one part will be mu naught I divided by 4 pi. R is A by 2 root 3. And sine 60 is root 3 by 2. So root 3 by 2 plus root 3 by 2 will be root 3. This root 3 will go up, that will become 3. Mu naught I divided by 4 by 2, I can write 2 here, pi A. So this is magnetic field due to one part of the wire. Other part will produce same magnetic field because this angle will be also 60, this angle will be also 60. So whatever I did, you repeat for this part also and this part also. So total magnetic field total will be 3 times this, because each part will produce same magnetic field. Direction is also same. So you can just add. So this will be 9 mu naught I by 2 pi A. So that would be the answer. Now if you substitute the values which are given, so total magnetic field is 9, mu naught value is 4 pi into 10 power minus 7. Current is given as 1 ampere, 2 pi, and what was the side? Side was 2 meter. So 2 2s are 4, so this 4 pi will cancel with 4 pi, so 9 into 10 power minus 7 Tesla. Okay, so which option it matches with? Option A. Option A. Fine. So simple application of the formula of magnetic field due to finite wire. So question number 2 is again based on the same concept, magnetic field due to finite wire, but the wire is kept in a different way. A infinitely long wire carrying current I is along y-axis such that one end is at point 0 comma b while the wire extends up to infinity. The magnitude of magnetic field at point P a comma 0. So first better to draw axis. So this is your x-axis, this is your y-axis. Okay. Now the wire is infinite and it is along y-axis. The wire is here. But it may be infinite, but one end is where they told at a point 0 comma b. 0 comma b means x coordinate is 0, y coordinate is b. So the wire is here. Okay. So this is your wire. Okay, the upper end goes to infinity. Upper end goes to infinity. Upper end goes to infinity. Okay, and this point, one end is at 0 comma b. So this is 0 comma b. Matlab this much is b. Correct? No, coordinate is measured from origin. Coordinates are measured from origin. And where is the observation point? Where we want magnetic field? At some point on x-axis. What is the coordinate? A comma 0. That means this much is A. Now let us calculate the magnetic field. What I told you to do, first you draw the perpendicular line. So this is the wire. This is the line of the wire. Right? This is the line of the wire. And please remember this is point A of the wire. Point B is at infinity. Then what I told you to do, first draw this perpendicular distance which is A itself. Right? Then you extend this line and other line will come like this only. Right? Why other line will come like this? Because other point is at infinity. Then let us remember once, if this is how the wire is, A here, B here, and this is your line, then you have to draw these two lines. This was theta 1 and this was theta 2. Right? Theta 2 was measured this way. Then I wrote magnetic field formula as mu naught by 4 pi I by this perpendicular distance, which is R or A, whatever you want to write, no problem. Sine theta 1 plus sine theta 2. Sine theta 1 plus sine theta 2. Now look here. Let us see what is theta 1 here. Theta 1 is the angle made by the upper end of the wire. Now upper end is at infinity. So if you draw this line, it will become like this, parallel. You all know, right? Parallel lines meet at infinity. So if these two lines are parallel, then this point will be at infinity, which is the case in this problem. So theta 1 is clearly 90 degree. Right? This is your theta 1. The angle made by this line. So theta 1 is 90 degree. Okay, upward only, right? Upward. Like this. Now theta 2, in my formula, I have shown this way. But here theta 2 will be this. Yes or no? So theta 2 should be taken to be minus of whatever is this angle. Let us call this angle phi. So theta 2 should be written minus phi. So what will be magnetic field? Mu naught by 4 pi I divided by R means this distance, or you can say this distance. So here it is A. Sine theta 1 is 90 degree plus sine theta 2 is minus phi. Okay. So sine of minus phi is minus sine phi. So this will be mu naught by 4 pi I by A 1 minus sine phi. So sine phi will be what from diagram? Sine phi will be, opposite is B, hypotenuse is this, right? Hypotenuse will be root over A square plus B square. So just substitute this sine phi here. So B by root over A square plus B square. So this sine phi I have substituted here. So it will be option B. Option B. Okay. A steady current I goes through a wire loop PQR having shape of a right angled triangle with PQ equal to 3x. So PQR is the wire which is in the shape of a right angle and right angle triangle with PQ equal to 3x. With PQ equal to 3x and PR equals to 4x and QR equals to 5x. So I think from this data it is very clear that this should be hypotenuse. This should be hypotenuse of the right angle triangle. Now if the magnitude of the magnetic field at P they want magnetic field due to the loop is magnetic field at P, they have given the answer K into mu naught I by 48 pi x. We need to find the value of K. So this K we have to find. So first let us draw the loop. Okay, let us draw a big diagram. So let us show it here. Okay, not very perfect. Now this shorter one should be 3x. This should be 3x. This should be 4x. And this should be 5x, right? Hypotenuse should be 5x. Now we want now QR. So QR, this is QR. Okay, and P should be here. So PQ you can put where? No, PQ is smaller, no? So PQ should be here. And PR should be 4x. So R should be here. Now current is in this loop. Let us say like this. They did not mention the current. Now at which point we want here? First understand, at this point this wire and this wire will not produce magnetic field, at this point. Why? Because this point lies on this wire also, this point lies on this wire also. Understood? So at P, magnetic field due to PR and PQ will be 0. So no need to calculate magnetic field here due to these two. Only due to RQ we have to calculate. And it is finite wire, right? Also, look here, one small thing you should know. If this is 37 degree and this is 53 degree, okay, then opposite to 37 degree you can write 3, opposite to 53 degree you can write 4, and opposite to 90 degree you can write 5. So this triangle is very useful in physics. It helps you to find sine 37, cos 37, sine 53, cos 53 easily. So if you look at the diagram that they have given, this angle you can immediately say how much it should be. See, this is 4x, this is 3x. So this angle should be opposite to 4x. Nah? So opposite to 4x, 53. So this should be 53 and therefore this should be 37. That we can immediately find. And why, sir, you are trying to find this angle? We will need all these angles because we have to find magnetic field due to finite wire. Okay. So basically we have to calculate magnetic field at P due to this finite wire. What is the rule I told? First draw the perpendicular line. Draw the perpendicular line, right? Then from those two ends draw this line. Already it is drawn. So this angle will be theta 1. This angle will be theta 2. Correct now? So just revise the part where I explained this. Okay. First draw perpendicular line from the wire. From the two ends you draw these lines which is already drawn. Then from this perpendicular line theta 1 here, theta 2 here. One is this side, one is that side. So both you can take positive as we have written in the formula. Okay. So let us calculate. Why did we want to be theta 1 now? Now you can immediately say what is theta 1 because this is 90, no? Perpendicular line we have to draw. So this is 37, this is 90, so this must be 53. And this must be 37. Correct? Theta 2 must be 37. So what is the magnetic field now? What is the formula? Mu naught I divided by 4 pi R or A, whatever you want to write. Let us write R here. Perpendicular distance is R. Sine theta 1 plus sine theta 2. So B will be R, we have to calculate. So let us try to find R. So how to find R? You can use either this triangle or this triangle, whichever you want. So for this triangle, 53 angle, R is the adjacent side and 4x is the hypotenuse for this triangle. Remember, if I write T here, then in triangle PRT, in this triangle, if I try to calculate cos 53, cos 53. This is your adjacent for this angle, adjacent, and hypotenuse is 4x. 4x. So R will be 4x cos 53. Correct? 4x cos 53. Check once carefully. So cos 53 you can find from here. Adjacent is 3, hypotenuse is 5. So this is 4x cos 53 will be 3 by 5. 3 by 5. So that will be 12x by 5. Try to use this triangle, same answer you must get. So this will be mu naught I by 4 pi r. What is r? 12x by 5 sine theta 1. Theta 1 is 53 degree. So this is 53 degree and theta 2 is 37 degree. Correct? No? So sine 53 degree will be what from here? Sine 53, 4 by 5. And sine 37 will be 3 by 5. This triangle is very useful, okay? So this 5 I can take up. 5 mu naught I, 4 2s are 8, 48 pi x, and here 5 LCM 7. Correct? So yours 5 will cancel, and now if you compare this magnetic field with the given magnetic field, mu naught I by 48 pi x, mu naught I by 48 pi x. So this 7 must be your K. So K must be 7. Okay. 4 very long straight parallel wires. 4 very long, matlab it is infinite. Located at the corners of a square of side L carrying equal current I naught perpendicular to the page. So if this is the page, current is perpendicular, either like this or like this, as shown in the figure. Determine the magnitude and direction of magnetic field at the center of the square. So first let me draw a square. Okay. So here current is going into. Okay. Here also current is going into. Here is current is coming out. Here current is coming out. Each current is same. I naught, I naught, I naught, I naught. They want magnetic field at the center. So since this infinite wire, we can directly use the formula of infinite wire. Mu naught I by 2 pi r. Mu naught I by 2 pi r. Now r is the perpendicular distance between the wire and the observation point. Now for this wire, this is your perpendicular distance. For this also, this is perpendicular distance. Same only it will be. This is perpendicular distance. This is perpendicular distance. Right? Wire is like this. So r is the perpendicular distance. Side of the square was given as L. So side is L. This is L. So this R will be how much? R will be half of diagonal. Diagonal will be root over this L square plus this L square. So L square plus L square. That will be root 2 L by 2. That will be L by root 2. So we have found R already in terms of given quantity. Now let us see, before we think of adding the magnetic fields, we have to check direction. So this is cross. So current is going inside. Right? So magnetic field will be like this. And how to draw the direction? I told first draw the radius. First draw the radius and then draw the perpendicular. So since this is a square, this itself will be perpendicular to this line. So this is magnetic field due to this. Okay. Cross means it is into, right? Into means you have to put your thumb like this. So curl of the fingers will give magnetic field. So here it will be like this. Similarly, due to this, it is into, so it will be like this. So here it will be here, this. Okay, magnetic field, this is due to this wire, this is due to this wire. Now this is out, so it will be like this. Okay, so magnetic field here it will be like this, like this. So when you reach here, the circle will be like this, so tangent. So that will be also here only. one more B will come. Magnitude will be same because each has same current and this distance is also same. And for this also it is out, so it will be like this. So when it reaches this point, the circle will be this much. So tangent will give you the direction of magnetic field. So one more magnetic field. So you can see there will be here now B plus B because same direction 2B, B plus B 2B in this direction. And this is also 90, right? Because this is 90 degree. Diagonals of a square are perpendicular to each other. So resultant will be here. This is your total magnetic field. So total magnetic field will be root over 2b square plus 2b square. That will be 4b square plus 4b square root 8b square, which is 2 root 2b. Now b is due to one wire. So due to one wire, you know the formula. Due to one infinitely long wire. Due to one infinitely long wire, what is the magnetic field? Mu naught I naught. Current is I naught, they told. 2 pi r. 2 pi this r. This r is how much we found? L by root 2. So L by root 2. Correct? Then root 2, this 2 and 2 will cancel. Root 2 will go up. So 2 mu naught I naught by pi L. 2 mu naught I naught by pi L. Next question is again very interesting. A long insulated copper wire is closely wound as a spiral of capital N turns. So there is a wire which they have wound like this in the form of a spiral. And how many turns are there? Total capital N number of turns. The spiral has inner radius A, so they are not starting from zero radius. Okay, it has some inner radius A and outer radius B. The spiral lies in the xy plane and a steady current I flows through the wire. The Z component of magnetic field at the center of the spiral. It will have only Z component only. I'll explain. So imagine this is your x-axis and this is your y-axis. Your spiral looks something like this. Okay. So it starts with some radius and then it goes like this. It is very closely wound. Okay, I cannot show you very closely wound. It's not very nice, I know. Something like this. Okay, so this is your spiral. So inner radius is A. Let me use another color. Inner radius is A. Outer radius is B. So this carries a current I, let's say. Okay, like this. This is Y, this is I, this is Y. So current I goes like this. So we have to find magnetic field here. And these are very closely wound, not like this. You can't see this gap. So it will look like a disc actually. So how to find magnetic field here? Quite simple. What we do, at some distance x, we will construct a ring of very small thickness. So this ring you have to concentrate. Okay. This ring you have to concentrate, the black one. So let me show it here. So this is the ring I have considered, very thin. So this is x and this thickness is dx. Now we can find magnetic field here due to this ring because you can consider this as a current loop because this dx is very small compared to x. However, how many turns are here, that you have to know. Without knowing the number of turns here, how will you write magnetic field at this point? There will be some number of turns in this dx. So we have to check how many turns are there. That is quite simple. Look here. In this distance, how many turns are there? They are told n turns. So in distance, this much, which is, this is B, this is A. So in this much distance, in distance B minus A, there are n turns. Yes or no? In B minus A distance, there are n turns, right? 1 turn, 2 turn, 3 turn, like that. N turns. So in unit distance, how many turns will be there? N by B minus A. This many turns will be there in unit distance. Okay, but I want distance in this much distance, dx distance. So therefore in dx distance, how many turns will be there? N by b minus a into dx. Okay, so this is basically like, how many, what is the cost of 3 apples if you know cost of 10 apples. So from the cost of 10 apples, find cost of 1 apple, then find cost of, how many apples I told? 4 apples, right? Multiply with 4. So I want to know number of turns in this small distance dx. So for that I need to know in this much distance how many turns are there that they have given. So in b minus a distance n turns, in unit distance n by b minus a. So in dx distance this many turns are there. Now once I know this many turns are there, the magnetic field here due to only this ring, I can consider this ring to be like a current loop with this many turns. Understood or not? And since it is dx, it is quite thin, so I can consider it like one current loop. So magnetic field will be what? Mu naught. What was the formula at the center of a circular current carrying wire? Mu naught I by 2r. So mu naught I, current is I everywhere, 2r. Radius of this is x. Don't write x plus dx. Even if you write dx is very small compared to x. So when you add, you can neglect, not when you multiply. And I must include number of turns. dn, let me say. This is the number of turns, dn. So dn is the number of turns in this current loop. So magnetic field, I can write this formula, and number of turns is what? N by b minus a mu naught I by 2 pi 2x, sorry, no pi because it is due to circle, into dx. Correct? So this is the magnetic field at this point due to one ring of this whole spiral. Now I need to consider such rings starting from this radius till I reach this radius. Correct? So total magnetic field will be what? This is magnetic field due to one small section of this spiral. So total magnetic field will be integration of this magnetic field. And why can I do directly integration? Because each ring carries current this way only, no? So it will be like this only. Everywhere magnetic field at the center will be like this. So since all the magnetic field due to different rings of this spiral are in same direction, we can just add. So it will be constants you take outside, n by b minus a, mu naught outside, I outside, 2 outside, integral of 1 by x dx. Now from where to where? Remember, not from 0 because the spiral starts from radius a. So when I am here, if I draw a ring, radius will be a. And when I am here, if I draw the ring, radius will be b. So from a to b. Now what is integration of 1 by x dx? What is integration of 1 by x dx? Log x. So this will be n by b minus a mu naught I by 2. This is log x. Put upper limit log b base e minus, put lower limit log a base e. So after doing integration, you have to put upper limit minus lower limit. This will be n by b minus a mu naught I by 2. This is log b minus log a is log b by a base. So this will be the total magnetic field at the center of the spiral. Question number 6, you see. A charge capital Q is uniformly distributed over the surface of a non-conducting disk so that the charge stays there only. Non-conducting disk of radius capital R. So this is radius capital R. From 0 to here is capital R, and it has charge uniformly distributed everywhere. Total charge is capital Q. Q is total charge. Since it is uniform distributed, what does it mean? Sigma will be constant. What is sigma? Charge per unit area. So Q by pi r square will be constant. Okay. Now the disk rotates about its axis. So at its axis means always this line, passing through center perpendicular to the plane. So it is rotating with angular speed omega. is rotating with angular speed omega. As a result of this rotation, a magnetic field of induction B is obtained at the center of the disk. So there will be some magnetic field here. Now you may be thinking why? Once it starts moving, there will be current. So that current will produce some magnetic field here. It is similar to single electron moving in a circle. That also produces magnetic field at the center. So this is obviously a disk which has charge. If it was not rotating, then there will be no magnetic field, because if it is not rotating, there won't be any current. But once it rotates, there will be magnetic field at the center. So if we keep both the amount of charge and angular velocity to be constant and vary the radius of the disk, then the variation of magnetic induction, matlab magnetic field, at the center of the disk will be represented by which figure? So they want relation between B as a function of radius. Basically, we need to find the magnetic field and check how the formula looks like. So let us start. Again, what we will do, same kind of thing. We will consider here a ring, a very thin. You can consider this whatever I have drawn, that itself is ring. Thickness should be this much. But let me, for clarity, let me draw one more line. So let me consider a ring whose radius is x, thickness is dx. Okay. Now let us see how much charge is only here. So only here, what will be the charge? So dq, let me say. So what will be the charge on that small part? Sigma surface charge density into area of this ring. So charge on this ring will be charge per unit area into area of this ring. Area of this ring, how many times I tell you? Cut this and open. It will be like a rectangle, almost like a rectangle, right? Like this. And this length will be the circumference of this, 2 pi x, and this thickness is dx. So this area will be the area of this ring, which will be how much? 2 pi x dx, right? Length into breadth. So that is the charge on this ring. Now it is rotating. Let me put my hand here, cross section. In one time period, how much charge will pass through my hand if it is rotating like this? Imagine my hand is some imaginary cross section. If I put imaginary cross section here, then in one time period, how much charge will pass through this cross section only due to this ring? This whole charge will pass. Yes or no? Whole charge will pass. So current will be di. This is the current due to the motion of this ring. Why I am dividing into rings? Because I know magnetic field due to current loop. Due to rings I know. Not directly due to disk, I have not taught you. So current due to this ring will be dq divided by time period. Very similar to when electron was revolving. If you take any cross section in one time period, charge of electron will pass. But here everywhere there is charge. Everywhere there is charge. So as you wait for one time period, the whole charge will pass through this cross section. The whole charge will pass through the cross section. Charge is how much? Sigma into 2 pi x dx. Time period in terms of omega, because omega is given. I can write time period as 2 pi divided by omega also. Either I can write 2 pi r by v, or I can write 2 pi by omega. It is the same thing. So 2 pi will cancel. So the current, small current in this ring due to the rotation of the disk, which is charged, will be how much? Sigma omega will go up x dx. Correct? Okay. So now I need to know what is the magnetic field at this point due to this current. So that will be dB, let us say. Mu naught, current here due to this ring, motion of this ring, current here is di divided by 2r. What is r for this ring? X, remember. Right? Okay. Then if I substitute the current di, how much I got? Sigma omega x dx. Very interesting, x got cancelled. So it is mu naught sigma omega by 2 dx. So that is your magnetic field at the center due to this ring. Now I have to find what? Total magnetic field. Now every ring has current this way ring. Once the disk rotates, every ring of this disk will also rotate like this. So current will be like this. So magnetic field everywhere will be in the same direction, right? So we can just add all the magnetic fields produced by the individual rings of this disk. So total magnetic field will be just integration of dB. No need to take components. Now this is mu naught is constant, sigma is constant, omega is constant by 2 integration of dx. From where to where? I have to start from this ring till I reach this ring, last ring, right here. So when I reach there, my x will start from, my variable is x, remember. So when I am here, my x will be 0. When I reach here, x will be capital R. So mu naught sigma omega R by 2. Now you may think, oh, that means B is proportional to R. But here in the question they told, if we keep the amount of charge constant, amount of charge and omega constant. So you have to write in terms of charge. So how to write in terms of charge? What is sigma? Total charge by total area, pi r square. Sigma is total charge by total area. So you can see one r will cancel, so it will be mu naught q omega by 2 pi r. So this itself could be one of the options. So you can see B is inversely proportional to R. So when R is 0, B is infinity. So the graph will look like this. When R is 0, B is infinity. And when R becomes infinity, B should become 0. So it is called rectangular hyperbola. Y proportional to 1 by x. So answer is option A. Listen carefully to the question. A hollow cylinder having infinite length. So there is a hollow cylinder which is infinite length and carrying a uniform current per unit length lambda. So lambda is something very interesting. It is current per unit length. Current per unit length. What does it mean? We'll see. Along the circumference as shown in the figure. So the current is along the circumference of the hollow cylinder. Magnetic field inside the cylinder they are asking, inside. So if you see the diagram, they have given you a cylinder like this and current is like this, okay? Everywhere. So it is flowing on the circumference. So if you think of this, it is like a solenoid. They want magnetic field inside. So you just turn this and keep it like this. Like this you keep it. Okay. So if it is going like this, then here it is going in, here it is coming out. So if it is like this, okay, if this is your cylinder and current is flowing through the circumference, so like this. So it will be like this, right? So here it is in, here it is out. Okay. So they want magnetic field inside. Now you know that this kind of current will produce, since it is infinite, here magnetic field will not be there. Just like in the case of solenoid I have explained. So magnetic field will be this way. Inside magnetic field will be like this. So this will be how your magnetic field lines look like. Just like exactly like solenoid. Okay. So if I want magnetic field at some point here, you have to draw one Amperian loop. And the best way to draw the Amperian loop is like this. This is my Amperian loop. Okay, so let us calculate. Let us apply Ampere circuital law. Line integral of B dot dl is equal to mu naught times current enclosed by the loop. Okay, enclosed by the loop. Now, what will be this part? Let us say this length is L. Now, from here to here, if I go like this, my B is this side. dl, in case of Ampere circuital law, dl is the small element of the Amperian loop. So I am moving this way, let us assume. You can go whichever way you want. So if I go this way, then here dl is this side, b is also this side. So I will get integral b dl from a to b, from a to b. Now from b to c I am going this way, dl is this side, magnetic field is this side. So dot product will be 0 because it's perpendicular cos 90. So this dot product will be 0. So due to this there will be no contribution to this integral, because for this part dl is this side. So dl is this side. Here there may be dl, but there is no magnetic field outside. So here there is no magnetic field. So again there will be no contribution to this integral. Then when I come this way, again there is no contribution to this part, because this dot product will be 0 for this part also. So which part will contribute to the line integral? Only a to b. So this is the left side of Ampere's circuital law. Right side is mu naught times current enclosed. Now, since magnetic field inside is constant, it is uniform, you can take b outside. And integration of dl will be L. Yes or no, from A to B. This length I have assumed L, right? That will be equal to mu naught times current enclosed. Now, lambda current enclosed means what? How much current is inside this loop? Remember, current is coming like this. Okay, like this. So imagine one loop here. So current is coming out here, out here, out here, out here. So this much current, whatever current is in this much length, that much current is only inside this loop. Agree or not? Only the current which is in this portion, only that current is coming out of this loop, remember. And I need to consider only the current which is inside this loop. Inside this loop, when I say, it means if this is the loop, current should come out from this surface of the loop. Okay. So lambda they already told is current per unit length, matlab for this length. So lambda is current per unit length. So if you multiply lambda with L, this L, you will get current in this portion, which is nothing but current inside. Understood? So L will cancel. So B will be mu naught lambda. Okay. Okay. The next question is question number 8. Diagram I have drawn already. So they are asking, a coaxial cable is made up of two conductors. Coaxial cable, okay, is made up of two conductors. So axes are same. Inner conductor is solid. So this is the inner conductor, and I am showing you the cable will be cylindrical only, right? But I am showing you from this side. So inner conductor, this one is solid and has radius R1. R1 is the radius of the inner conductor, and the outer conductor is hollow of inner radius R2. This inner radius of this outer conductor is R2 and outer radius is R3. So this is one conductor, this is one conductor. The space between the conductor, this is air. Okay. Then they are saying the inner and outer conductors carry equal and opposite current. So if this conductor carries I current, this conductor carries I current this way. Okay, everywhere. Total current is I, let us assume. They want the variation of magnetic field with distance from the axis. So they want how magnetic field will vary as you go away from this axis. This is the axis, no? Because this is the cylinder. So if this is the cylinder, this will be the axis. So basically, okay, this is the central line. This is the distance from the center. So let me write small r as distance from the center. And here magnetic field. So how it will look, that we have to draw. So let us discuss. So first let us say I am at some point here. Then what I should do? I should draw one Amperian loop. Yes or no? So let me draw one Amperian loop like this. This is my Amperian loop. Then I will apply Ampere's circuital law. Distance is small r. This is small r. Okay. Or if I draw here, this is your inner conductor whose radius is R1, and I want first magnetic field somewhere here. So what was the technique? First you draw a Amperian loop passing through that point, and distance from the axis of that point where I want magnetic field is small r. Then you apply Ampere circuited law. Now the left side will be what? B into 2 pi r, right? Integral of B dot d B dot dl. So dl is along the loop, and since magnetic field will be circular only because the currents are either coming out or going in, so magnetic field, even if it is there or not there, it has to be circular. So magnetic field here is circular, loop is also circular, so B and dl will be in same direction. So integration of B dot dl will be B dl cos 0. Then B you take out, integration of dl will give you the length of the loop, which is 2 pi r. Already I told you in regular class also, try to remember the left side of Ampere circuital law like this, if magnetic field lines are circular. Okay, this should be equal to mu naught times current enclosed by this loop. Now can I say the total current capital I in this conductor is the total current inside? No, only this much current I want. So what will I do? B into 2 pi r equal to mu naught, and current inside will be only this much, that will be total current is capital I, total area of this is pi r1 square. So this is the current density in this conductor into area of the inner part, pi r square. That will be the current inside. Yes or no? So this is your J into this area will give you current in that area. So one R you can see will cancel. Other things are constant in this problem. So magnetic field is proportional to R. In class also we have done this part. So as long as you are inside this is your R1, let us say, this is your R2, and this is your R3. As long as you are inside this conductor, your magnetic field will be directly proportional to distance from the center. So it will be a straight line like this. Okay, as long as you are inside. Okay, fine. Now, once I reach here, how will the magnetic field change? Now, once I am here, this point, then again I have to draw Amperian loop. So let me show separately. This conductor is with radius capital R1, current is capital I. Total current in this conductor is capital I. Now I want magnetic field somewhere here this time. So I will draw this loop. Then apply Ampere circuital law. At what distance? R from the axis. Left side of Ampere circuital law will be B into 2 pi R. Right side will be mu naught times current enclosed. Now this time I can say the total current is inside only. No need to find any part. No need to find part of the current because total current is inside this loop. So total current I. So now you can see magnetic field will be mu naught I by 2 pi R. So it is inversely proportional to R. So outside the graph will be inversely proportional. So graph will decrease like this. Now if this conductor was not there, it would have gone like this and become 0 finally. If this conductor was not there, the magnetic field will keep decreasing and become 0 according to this formula. But once you reach here, matlab somewhere here, how will magnetic field look? That also we have to check. Now what will be my diagram? This is my inner conductor, this is my outer conductor, and this is the outer surface of the outer conductor, right? This is R1, this is R2, this is R3. And right now where am I? I am somewhere here. Right? Okay, so what I should do again, draw a Amperian loop. Okay, so left side will give me B into 2 pi R. Right side will be mu naught times current inside, current enclosed by this loop. Now here total current is coming out I. Here total current is coming in I. Now what is the current inside this loop? This much is inside, no doubt. So it will be B into 2 pi R equals to mu naught I is inside, and this much part also we have to calculate. This much part. Now how to find current through this much area? Simple, multiply current density with this much area. Minus or plus here? Minus, because this current is out and this much current will be in. So they will subtract. So minus J into this area. Now this area how to write? Pi. This bigger area will be, this is your small r. No, wherever you want magnetic field is small r. Remember, we are plotting graph of magnetic field versus distance from the axis. So when you want magnetic field here, this is your small r. So this bigger area is pi r square minus this area will be pi r2 square. Pi r2 square. Correct? Fine. Okay. Now what will be J? Remember, J is now for the outer conductor. So J will be total current, which is capital I only, divided by total area of this outer conductor. Total area of the outer conductor will be pi r3 square minus pi r2 square into pi r square minus pi r2 square. So this is how the magnetic field will vary. Then you can bring this 2 pi r this side. Okay, so the formula looks very complicated. So directly to decide whether it will, one thing is clear, it will decrease only because there is minus sign here, so it will further decrease. But how it will decrease, where it will go, that how to check. Do one thing, check when you reach here, when you reach there, what will be magnetic field when you reach there. So when you reach there, what will be your small r? When you reach here, small r will become r3. Yes or no? So when small r becomes r3, what will be your B? Check. When small r is equal to r3, if I put r3 here, this will be pi r3 square minus pi r2 square divided by pi r3 square minus pi r2 square. So this and this will cancel. I minus I, that will be 0. So when you reach here, magnetic field should be 0. So it is very clear, the graph cannot go this way. So the graph should come like this. Okay, option C. Okay, option C. Okay, let us see now question number 9. A wire B of finite length capital L is kept on right hand side of a long wire capital A as shown in the figure. So capital A represents one wire which is very long. Very long when I say infinitely long. Carrying current I1. This carries current I1. Okay. And a wire B of finite length capital L is kept on the right side. So there is a finite wire like this, perpendicularly it is kept. This length is capital L. And this distance they have not shown properly. This distance is B. Okay. You have to find direction of the currents on both the wires is shown. So this carries current here, I2. Suppose F is the force on the wire capital, then we have to find the formula for force and we have to decide the torque is clockwise or anti-clockwise. Now this is not parallel wires. If you remember, for parallel wires, if two very long wires are there parallel, then the force on one wire by the other wire was mu naught I1 I2 by 2 pi r into L. L is some part of the wire which you are using to find the force on. So if you want to find force on this part of the wire whose length is L, this is the force. So this we have derived in our board syllabus. But here this wire is kept perpendicular. So first of all you have to understand that different parts of this wire are at different distance from this wire. Yes or no? Different parts of this are at different distance. So whatever magnetic field this wire will produce, that will not be same everywhere. So directly we cannot use ILB formula. So what we need to do is at some distance x from this wire, let me consider a small section of this wire, small section. whose thickness is dx. So the small dx, this part, let's say the length is dx. Okay. Now, what will be the magnetic field here? Magnetic field here due to this current will be mu naught I1 by 2 pi x. Why x? Because this is the distance of this part from this wire. And we know the formula for magnetic field due to a infinitely long wire at a distance r or a or x. So at this distance x, this current carrying wire produces this much magnetic field. Direction will be where? Into. Right? This magnetic field will be into. Now consider this small part. This small part has length dx. Length dx. It carries current this side I2. Current is this side I2. And magnetic field here is into the board. So this small part can be considered as straight wire. So you will feel a force. What will be the force? df. I, current in this wire which is I2, length is dx, into whatever magnetic field it is experiencing, which is produced by this wire. You can add b1 if you want. So b1. Understood or not? Okay. Now sine theta no need to write because magnetic field is here, dx is here, and dx will be taken along the current, right? So it will be 90 degrees. So no need to write sine 90 degree. So then you can substitute the magnetic field is mu naught I1 by 2 pi x. So this is the force on this part. Where will be the force? Current is here, magnetic field is in. So L cross B, force will be upward. So force on this will be upward. Yes or no? Okay. What about force on this part? Well, current is here, magnetic field is here due to this. So force will be upward only. So at every part, force will be upward. So no need to take components, directly we can integrate. So total force will be integration of df. Because all the df matlab all the force on different parts of this wire are in same direction upward. So you can directly integrate. So if you integrate, what will you get? Constants you take outside. What are the constants? Mu naught I1 I2 divided by 2 pi. What is left? 1 by x dx. Correct? No, 1 by x dx is left. Now I have to find force on this part till I reach this part. Correct? Because question was to find force on this wire due to this current or this wire. So when I am here, what will be my x variable? D. And when I reach here, what will be my x variable? D plus L. D plus L. So that is how I should find the limits of integration. Then you know already integration of 1 by x dx is log x. So this is mu naught I1 I2 divided by 2 pi. Integration of 1 by x dx is log x. Put upper limit log d plus L minus log b. Then use the formula log a minus log b base e. So this will be mu naught I1 I2 divided by 2 pi log base e d plus L divided by b. So that will be the force. So let's check the force matches with which option. Mu naught I1 I2 by 2 pi log L plus d by d. L plus d by d upward. Force is upward. So option A. Force is upward. What about torque? Will this wire feel a torque? Think carefully. This part I told will feel a force df. This part will also feel a force df. But df, what I wrote? Df. I dx b. Yes or no? Now b here is more or b here is more? B here will be more because this part is nearer to this wire. So magnetic field produced by this wire is inversely proportional to distance. So when you are nearer to this wire, magnetic field here will be more than here. So this force I is same, dx is same, but this B is more here than here. Understood or not? So therefore this part will feel more df than this part. So if that means if I write this as df1, this as df2, then df1 will be greater than df2. So basically this wire will feel greater force this side than this side. Understood? So it will go upwards because it is feeling a net force upwards, but also it will rotate like this. So the whole thing will feel this kind of torque. This kind of torque means clockwise. Right? Clockwise. So in question number 10 they are saying a long horizontal wire AB rests on the surface of a table and carries a current I. This is long wire AB. It carries a current I. Okay. Horizontal wire CD is vertically above the wire AB and is free to slide up and down on two vertical metal guides C and D. Wire CD is connected through the sliding contacts to another wire such that it also carries a current I. Now if you see a diagram, you will see that there is one part here which can move up and down because there are some screws here. Some screws are there like this. Some screws are there, and this wire can move up and down. Okay, and it carries current this way. Okay, so this is how it is. Current is coming here like this, and that current is also I. So current I will go like this, like this, like this. So here current will be I. Okay. Now the opposite in direction to the current in wire AB. So compared to this current, this is opposite. Now the mass per unit length of the wire CD. This is your CD. So for this mass per unit length is given lambda. Question is, to what equilibrium height will the wire CD rise, assuming that the magnetic force on it is due to the current in the wire AB? So we know that these two, look these two carefully. These two are parallel wires, but they carry current in opposite direction. Like currents attract, unlike currents repel. So this is unlike currents, opposite direction. So these two will repel. This is on table. So this will not go anywhere. So this will jump to some height. So let us say this height is h. So this will be repelled by a magnetic force. Magnetic force. Now in equilibrium they told. So in equilibrium what should happen? This magnetic force should be balanced by mg. The magnetic force felt by this part of the wire whose length, let me say, is L. Okay, let me write here, length of this part is L. So the length of this part is L. So this part will feel a magnetic force because of this wire. Yes or no? You can check the direction. See, this will produce this kind of magnetic field outward. Outward. So magnetic field is outward. Current is going this side. So force will be up. This immediately you can check. So this part is feeling magnetic force upward. In equilibrium, what is this height up to which it will rise, they are asking. So in equilibrium, this magnetic force must be balanced by this mg. Correct? Now what is magnetic force? This is parallel wire. So for parallel wire, standard formula you apply. Mu naught I1 I2 by 2 pi this distance, which is h, into L. You remember that, no? This L equal to mg, because we want force on this length of the wire. So we have to multiply. This is L. So here currents are same in both of them. So I can write I. So if you cross multiply, what will be your h? So mu naught I square L will be mg 2 pi h. Cross multiply. So your h will be, the height up to which it will go will be mu naught I square L by 2 pi mg. Now they gave you mass per unit length of this CD wire is lambda. That means mass will be what? Mass will be lambda into L. So in place of mass, you can write lambda into L into G. So L will cancel. So that much height it will rise in equilibrium. So in question number 11, they are saying two parallel wires in the plane of the paper are x naught apart. So two parallel wires are distance x naught apart. A point charge is moving with speed u between the wires. Point charge is moving between these wires with speed u in the same plane at a distance x1 from one of the wires. Now which wire they have not told. So at a distance x1. So here some charge q is moving with speed u. When the and it is moving in what direction they have not told. So let us continue. When the wires carry current of magnitude I in the same direction, the radius of the curvature of the path of the point charge is r1. So this time the radius of this charge, not radius of this charge, radius of the curvature. Now you know that, see, this will produce magnetic field like this here. This will produce magnetic field like this here, right? So this is magnetic field due to this part. This is magnetic field due to this wire. Yes or no? Check once. In, this is out. So since magnetic field is perpendicular, either this or this, and this charge is moving in this plane with some velocity u, it is very clear that when charge moves in a perpendicular magnetic field, what I told first session, it moves in a circular path. So radius of that curvature is given r1. Okay, when the currents are in the same direction, and it is moving at a distance x1 from one of the wire. Now, in contrast, if the current in the two wires have opposite direction to each other, if currents are in opposite direction, so here I, okay, the radius of the curvature is r2. So at same distance x1, when this charge is moving with speed u, now the radius of curvature is r2. Find the value if x naught by x1 is 3, then find the value of r1 by r2. So very simple. What is the formula for radius? mv by qb, right? So under what magnetic field it is moving when it is here? When it is here, what is the magnetic field? Let us calculate. Due to this current, it will be mu naught I by 2 pi this distance x1, correct? And due to this wire, it will be mu naught I by 2 pi this distance. At this point, I want magnetic field because the charge is moving here. So that time, where whatever is the magnetic field, that will act on the moving charge. So what is this distance? X naught minus x1. So that will be x naught minus x1. So this is the magnetic field when the currents are in same direction. Here in, here out, here out. Due to this it is out, due to this it is in, correct? Okay. So since the magnetic field are in opposite direction, I should put minus. Okay. So let us check due to this later. Now they also told x naught is 3 times x1. X naught is 3 times x1. So I can write, let me remove this also. So magnetic field will be mu naught I by 2 pi x1 minus mu naught I by 2 pi. X naught is 3x1. So it will be 3x1 minus x1 will be 2x1. Correct? This is 3 times x1 according to the question. So magnetic field will be what? Mu naught I, let me write this magnetic field, mu naught I by 2 pi x1 common, 2 pi x1 common, 1 minus half, 1 minus half, 1 minus half will be half. So if this is half, you will get this as 4. So this is the magnetic field right now. Okay. Now when the currents are in, let us call this equation 1. When currents are in opposite direction, what will happen now? Look carefully. This will produce in only, but this will produce now. This will also produce in because current is this way. So here it will be in. So both are in. So now the magnetic field will be second case. Magnetic field total will be what now? This plus this. Matlab this plus this. So mu naught I by 2 pi x1 plus mu naught I by 2 pi 2x1. So now it will be plus. Distances, everything are same. Current, everything is same. Only they have changed the direction. So it will be now half plus 4. No, it will be 4, 2 plus 1, 3 by 4. So 3 by 4 mu naught I by 4 I wrote already pi x1. So this is the magnetic field in the second case. B dash, let me write. Now what is the formula for radius of curvature? mv by qb. V is same, mass and charge are same because same particle only is moving, but in the two cases magnetic field is different, correct or not? So radius in the first case divided by radius in the second case will be magnetic field in the second case, which I wrote B dash, divided by magnetic field in the first case, correct or not? Inversely proportional na. So radius in the first case divided by radius in the second case will be magnetic field in the second case, which I wrote B dash. So this ratio, if you calculate, everything is same. So this will be 3 by 1. Other things will cancel. See, this part is same as this part. Okay. A uniformly charged disk of radius small r. So there is a disk of radius small r having charge q. So total charge is q uniformly. Q rotates with angular speed omega. What is the magnetic dipole moment? Magnetic dipole moment. Magnetic moment, let me write. Now again, what you can do this is by making here a ring, then wait for one time period. The charge of the ring will pass through any cross section. So current of any one ring here will be dq by capital T. Just like I found magnetic field at the center. So that way you can do it. First find the current, then find the magnetic moment. Current into area of that ring, pi x square. Because that ring which I took was having radius x. So this way you can do, then you integrate to find the total magnetic moment. Like this we can do, but we will apply one shortcut. There is something called gyromagnetic ratio, which says magnetic moment divided by angular momentum. Magnetic moment divided by angular momentum is always equal to charge divided by twice of mass. Charge divided by twice of mass of the object. Here the object is a disk. Now be careful, this m, this m. So let me write here capital M. So this is mass. So this formula, if you can remember, then just cross multiply. Magnetic moment will be what? Charge divided by twice of mass into angular momentum. Now it is a disk which is rotating with angular speed omega, and you know angular momentum formula is I times omega, where I is moment of inertia. Be careful, not current. Moment of inertia. So sometimes different concepts will have same symbol. So what is the moment of inertia for a disk? Moment of inertia for a disk is mr square by 2. So substitute this. So magnetic moment will be q by 2m into mr square by 2 omega. So m will cancel. So it will be q by 4 r square omega. Q by 4 r square omega. Q by 4 r square omega. Option A. Since you already know formula for moment of inertia, this calculation will be very easy if you remember this general formula. So no need to do all this integration, which will take time. They are saying wires 1 and 2 carry currents I1, I2 respectively are inclined at an angle theta. to each other. So one wire is like this and other one is here. Okay, this one let me show later. This is the second wire. First wire, second wire. They carry current I1, I2 at angle theta. Okay, so what they are asking, what is the force on a small element dl of wire 2 at a distance r from the wire? So there is a small element somewhere here. Let me dark that part. Small element dl which is at a distance r. So what is the force on this they are asking? Due to the magnetic field of this wire. So the magnetic field of this wire will exert force on different parts of this wire, right? If it is parallel, we know the formula directly. Assume the angle made by the line from the top end to dl is also theta with wire 1. So matlab from here if I come like this is also theta they are saying. Okay, that is not given directly, okay, so you have to check carefully. So the line from top end of the wire to the small element where we have to find the force, on which we have to find the force, that one also makes angle theta with this wire, I1, first wire. So how to find the force on this? Simple, they are not asking you to find force on the whole wire. Whole wire means you have to integrate, like I did this kind of wire. So one was perpendicular to first wire. So you don't have to integrate to find force on the whole wire. You have to find force on only this part. So let us look at this part. This is dl. Current here is I2. So we just need to calculate magnetic field at this location, matlab at this location due to this wire. This is a finite wire, so we have to use the formula mu naught I1 because we are calculating magnetic field due to this current. So mu naught I1 by 4 pi, perpendicular distance already it is given r, sine theta 1 plus sine theta 2. Now be careful with who is theta 1 and who is theta 2. This is your theta 1, correct or not? And this is your theta 2. So now if you check, this is theta. Answer should be in terms of this theta. So this theta 1 will be what? 90 minus theta. And this theta 2 will be 90 minus theta. Correct, no? This is 90 degrees, 90 degree, 90 degree. This is theta. So this other angle will be 90 minus theta. So here I should write 90 minus theta. 90 minus theta. And here I should write 90 minus theta. Plus. Okay, students. So once you have done that, then it's very easy. Mu naught I1 4 pi r sine 90 minus theta cos theta. This is also cos theta. So 2 cos theta. So that is the magnetic field produced by the first wire. Let me call it B1. Now that B1 will be in what direction? Into the board. So into the board. Correct? Current is on this second part, second wire, current is this side. So force on this part, dl part will be what? Force on this part we want. So current in this part is I2, length of this part is dl, and magnetic field here is B1, which is produced by this wire. So B1. So it will be I2 dl. What is B1? These two 2's are 4, you can cancel. So mu naught I1 cos theta divided by 2 pi r. Then you can rearrange and write dl at the last. I did not write sine theta here. Why? Because see, dl is here along the current, magnetic field is inside the board. So it's 90 degree, no? Understood or not? And where will be the force if they ask? Magnetic field is inside the board, current is at some angle, so force will be this way. So if they ask direction also, we can find. Okay, students? So in question number 14, they are saying, determine the magnitude of magnetic field at the center of the current carrying wire arrangement shown in the figure. The arrangement extends up to infinity. The wires joining the successive squares are along the line passing through the center. But if you look at the diagram, you will find no that there are squares. And the small gaps which are there, you have to neglect that gap. You have to neglect that gap. So basically, if you look the diagram, you will be having one square here, then one more square here, and one more square here like that. Forget about the gap. Okay. So if you forget about a small gap, you will find squares. The first one has side A, second one has side 2A, third one has side 3A, and it goes up to infinity. And current is flowing. Actually, it comes like this. So it comes like this. So current here is like this. Okay. Then it is joined to this part like this. So it goes like this. Then this is joined to this part like this. So current goes like this. Then it is again joined to another part like this. Okay. So that way it keeps on building. So you have to neglect the small gaps. So what we will do, we will calculate magnetic field due to one square first. That is very easy. So think of one square, the innermost square, this part. Let me make it bigger and show you here. This is A. This is also A. Correct? So at the center they told. Current is going this way. Okay. Forget this small gap here that you have to neglect. Okay. So now let us calculate magnetic field due to this part. You know what to do. First draw this perpendicular distance R. Then from the two ends draw this one. And this angle is theta 1. This angle is theta 2. Theta 1, theta 2. And here you can see both of them are 45 degrees. Why 45 degrees? Because this is 90 and this is bisecting 90 degrees. Nice? Yes or no? This is 90 and this is bisecting 90 degrees. So this is 45, this is 45. So magnetic field here due to only this part will be mu naught by 4 pi I by R sine theta 1 45 degree plus sine theta 2 45 degree. Right? Okay, what is R here? This R is very simple. This is A, this is R. In case of triangle, we had to find the distance from the centroid to one side of the wire. Here no need to do. From center to one side of the wire, this will be half of A. So R will be your A by 2. Okay, let me write next step. So mu naught by 4 pi I A by 2. 2 will go up. Sine 45 plus sine 45. 1 by root 2 plus 1 by root 2. 2 by root 2. So root 2. Correct? No. So what is the magnetic field due to only one part of the wire? This much. Now there are 4 wires. Then direction will be where? Due to this out. Due to this here out. Due to this here it will be out. Due to this one it will be here in but here out. So all of them are out. So magnetic field is out. So the magnetic field due to the first square will be 4 times this. 4 times this is due to each part. Okay. This is magnetic field due to each part. There are 4 parts. So total magnetic field will be 4 times this. So mu naught by 4 pi 2I root 2 by A. 4 cancel. So 2 root 2 mu naught I by A. That will be magnetic field due to the first square. Now due to the second square, so due to second square, magnetic field will be what? Only difference is before the side was A, now the side is 2A. So it will be 2 root 2 mu naught I by 2A. Due to the third square, what will be magnetic field? Everything is same 2 root 2 mu naught I, but side is 3A. So like that up to infinity they told. Now direction you please remember. So for this current it is out. This was out. But for this one, second one, you can see current is here like this. Right? Did I do correctly or not? Oh, this was like this. Sorry. Sorry students, if I look the diagram carefully, current must be coming this way. It is going like this. So here it is coming like this. So here it must be like this, like this, like this, like this, right? Then only it can go this way. No, here. Correct? No? Okay. So now you can check. Due to this inner part, it is in here. In. So this is in. Okay, the one which I showed is correct only, but their current I took this way, but actually current is going this way. So due to this in, due to this in, due to this also in. So due to the first square, magnetic field is in. Due to second square, you see. Due to this current, this part you see out. Due to this out. Due to this out. Due to this out. So this is out. Again due to third one will be in. See, current is this side in. So this will be in. So this, if I take this positive, this is positive, this will be negative. So total magnetic field will be B1 minus B2 plus B3. Then next is minus B4 plus dot dot. So common you take outside 2 root 2 mu naught I by A. One will be left here. Then next one here what will be left? Minus 1 by 2. Here what will be left? Plus 1 by 3. Next what will be left? Minus 1 by 4 plus dot dot. Okay, and this series is what we learned in mathematics to be log 2. This series is log 2 base E. So option will be 2 root 2 mu naught I by pi A. Pi A, how come pi A? Oh yes, there has to be pi because there is pi here. See, mu naught by 4 pi. So there is pi here. And here also pi will be there. Here also pi will be there. Right? So I missed pi. Okay, one last topic I want to do, and that is magnetic field due to sheet of current, which is infinite sheet. Okay, so you have to think, if this kind of sheet of current is given, so imagine current is coming like this towards you. Okay, so current is along the sheet, and we want magnetic field somewhere here or maybe here. So what will be the magnetic field at a point due to a sheet of current? Remember, current is flowing this way. Infinite sheet, you can imagine. So this is very similar to electric field due to sheet of charge, but this is magnetic field we have to find due to sheet of current. Okay, and since current has to flow, so you can imagine, uh, infinite wires kept close to each other from here to here. So infinite wires you imagine which are kept close to each other from here, from starting from here till here, like that. So let me show you only this side. Okay, this side, this part I will show you. Okay students, so this is a sheet, and let's say current is coming out. Everywhere you think the same thing, and it is infinite. Okay, I want magnetic field at some point here. First, as I told, you need to have idea about how magnetic field lines look like. Now imagine there was only one wire like this. Only one wire was coming out. So if only one wire was coming out, magnetic field will look like this. Is it not? Like this. But another wire is also there very close to. Actually, these are just wires kept. These are just parallel wires kept, you know, very close to each other, so that you can consider this like a sheet. So if you consider the next wire here, immediately next, but let me show you here. This will produce magnetic field this way. So you can see here these two magnetic fields are in opposite direction. Correct? No? So they will cancel. So basically in the middle part the magnetic field will cancel due to all these currents, and here due to this it will be like this, here due to this it will be like this, due to this like this. So in the outer one, in the upper side, you can say the magnetic field will look this way. Okay. Similarly, here you can say downside, the below this wire, below this sheet actually, you can say magnetic field will look like this, right? Below. So this is how, by symmetry, you can guess how the magnetic field lines will look like. So now, it is quite easy to solve this problem now. We have to find magnetic field at some point here. So I need to draw a Amperian loop passing through that point. So the best way to draw the Amperian loop is this, right? So this is my Amperian loop. Let me call it PQRS. And I want magnetic field at some point here. So I need to do the integral of B dot dl along this closed loop. So when I move from here, magnetic field is this way. Right? This is the red color. Magnetic field is this way. dl bar in Ampere circuital law is always along the loop. So dl bar is also here. Magnetic field is also here. So it will give me B dl from P to Q. And here it will be 0 because my dl is this side, magnetic field is here, and for this part I'm going this side, magnetic field is here, so perpendicular dot product will be 0. From here to here, magnetic field is this way, I have to move this way, right, in the loop. Whichever way you move, it's your wish. So these arrows are basically your dl vector. Understood or not? So here I will get another b dl, cos 0 will be 1 from R to S, and here again it will be 0. So this will be the left side of Ampere circuital law. Since magnetic field is uniform here and here, you can take B outside. Integral dl from P to Q, from P to Q. If you integrate dl, you will get total length. So let us say this length is L. So L plus this will be also B will come out. So this will be L. Okay. So this will give me 2BL. Just like if you remember, we used to get 2E like that. 2E, what did we get? 2E A. Because there we were integrating on a surface in Gauss law. Okay. When we applied for sheet of charge. So now once we found the left side of Ampere circuital law, 2BL, now we need to know current inside this loop. So you can see this current is inside, this current is inside, this current is inside. So if this is your sheet, current in this much part is inside, right? This loop. This is the loop which I have considered. One here, one here, one here, one here, one. This is the loop, right? So you can see this much current is inside the loop. So how to find that current? For that we will define lambda, which I will say is current per unit length. Current per unit length. Meaning you take some length, see how much current is flowing through that length, then divide the current by the length. That is your current per unit length. So according to Ampere circuital law, this should be equal to mu naught current enclosed. Current enclosed, right? So this should be equal to mu naught times current enclosed means current in this length. This is lambda, which is current per unit length. So lambda into this length. That will give me current enclosed. This is my current enclosed. Okay. So from here L you can cancel. Mu naught current enclosed. Mu naught current enclosed. And current enclosed is lambda into L. This will be equal to L cancel. 2B will be equal to mu naught lambda. So B will be mu naught B will be mu naught lambda by 2. So this is the magnetic field at some point due to a sheet of current. You can see it is a uniform magnetic field. Just like for solenoid, it is a uniform magnetic field.